Hello, Caitlin. Hi, Josh. Or Joshua, if you prefer.
Sir, how you doing?
All right, how about yourself?
Not bad. Apologies for missing the the first ones. The first one I completely forgot about. The second one I set a timer for, and I don't know. It was just the one class, video class a week kind of threw me off, and so
Gotcha.
I made sure I got to this one.
Good deal. I am. If this works out, I've started the classes that I have on Tuesday for my class in North Carolina. I've opened that up to you guys, and similarly, I've opened this class up to them. So we'll be able to meet twice a week if you want from now on. That's 10 to 10 o'clock time at Tuesday and Thursdays. So I'll make sure everybody's invited to all those. I did have one person last time, so I know it works that way. I'm not sure if it's going to work this way. Caitlin, you're from here at TCC, right?
I'm sorry.
Are you from TCC or are you from College of the Albemarle?
Oh yeah, I'm with TCC.
Okay. I didn't remember seeing your name on the COA roll, but I'm not very good with keeping up with names, so it could have been either way. But yeah, so basically I have a class going at, we weren't sure we were going to be able to have summer classes, so I took a job this summer teaching at my old school. And so I've got two classes going at one time, but I figured it'd be nicer if I could basically pull the resource and have 2 meetings a week instead of 1 meeting a week, just by sharing everybody's meetings. So you now can meet on Tuesdays at 10 and on Thursdays at 10, but all of them are optional. You never have to come, of course. What I usually end up doing is I take questions for usually the first 10 or 15 minutes and then go into a lecture material. And several students stick around and ask questions and stuff, and that's great if you do want to do it, but you're not required to.
I would have been here on Tuesday, but I was called in to help pack up my classroom.
Gotcha.
Yeah, I'm a paraprofessional. Yeah, so it was the day that my teacher was going to be there, so I helped pack up the classroom that morning.
Gotcha. Well, does anybody have any questions about how the course runs? I mean, I know it's really late. I should know that by now, but there's always some stragglers not necessarily understanding all the details or about course material in general.
I have a couple questions.
Go for it.
So so I remember seeing a place for this Heavens Above lab that we have to do.
Right.
I remember seeing somewhere that it said that you could go to learn how to read the sky chart. Is it?
You could just Google it, but I can give you the rundown on it. So a sky chart really, and you can buy these. They have them at like Barnes and Noble and various art or school supply stores and stuff like that. But they're basically usually a disc that shows. If you could see all of it at once, you'd see all the possible stars that we see from about 30 or 40 degrees latitude. Each one's made it for a different latitude, but they're usually 30 or 40 north. And so it allows you to see basically the disk is as if the stars are all on a flat plane, and it covers a little bit more than the northern half of the celestial sphere, which obviously doesn't exist. But when you dial it to a certain date and time, the window only allows you to see what's visible from that location at that date and time. But the weird thing is, if you look at it, the top says north, and then off to the right, it's west instead of east. That's what you're meant to hold it over top of your head like this. So if you point the north forward like this, then you turn and look to the north, which is where the North Star is. Then the right-hand side, of course, would be the west, and the left-hand side would be the east, and it would make more sense to you. Okay. So that's all it is. The big thing is when you look at that, you got to remember there's normally a little pinhole thing that allows the object to rotate. There's a little pinhole in the actual sky chart, which you aren't using. You're using a software package, but that's right near Polaris. And the actual center, the apex of the night sky, i.e. what we call the zenith, is the center of the oval that you see, or in the case of the sky chart, it's the center of that whole circle. That whole circle, the center is directly overhead, and then up here is north, and then over here is east, or excuse me, west, and then east, and then south. And that ring around the outside is the horizon. So it's kind of weird because if you're looking over here at this side, this line points from the circle towards the center is actually vertical. Like if you were standing on the horizon there, you would see that as vertical. So you got to keep that in mind when you're trying to think about whether something's moving up or down. If it's getting farther away from the circle, then it's moving up. If it's getting closer to the circle, to the gray circle around the edge, then it's moving down.
So it'll be, okay, my thing was, because I started to do some of the questions, I didn't write anything down yet, but I was just trying to look at it. So because east is on the left side and west is on the right side, if you're going, so from my point of view, the star starts going, this is probably wrong, but I'm just saying as an example, if it starts going to the right, then it's technically going to the left.
No. Okay, I got you. Yeah, let me explain that to you right quick. Actually, this is a really good question, especially since we're doing that lab. I'm going to share my screen with you and pull up Heavens Above so y'all can follow what I'm talking about. This will be helpful for everybody. So I'm going to do share screen, and let's share this one. Okay, now heavensabove.com. Minimize this to get it out of the way. Notice I'm not signed. Oh, actually I am signed in. That's pretty close to where I am. I can't remember if I put that in for Virginia Beach or here, but it's pretty close to what y'all have. And we're literally as far away as I am versus the school. That would be plenty accurate. So don't worry too much about putting your exact location. You know, a lot of people are very private about where they live, and you know, for good reason, because there's crazy people, and you know, these videos are gonna be on the internet, so don't share that with you with me. So anyways, interactive sky charts, what the one I like to do. If your system don't work with it, use that old version. So here's the actual star chart. I can't make it any smaller that I know of anyways, but the key thing is you see north is here, and west is over here, south is back here, and east is over here. So yeah, it's meant to be held overhead, but right and left doesn't change. So for instance, remember when I did the sky chart, I said if you look to the east, stars go up and to the right. So right now, this little star right here, called star evidently, this little star is essentially due east. Remember, vertical is straight up and down. So from here towards the center is straight up. And right would be this way. So what I'm going to do is I'm going to advance it forward 1 hour. Hopefully, yes, I can still see it. And I think you'll see it move up and to the right. There you go. See, it went from directly over here to over to here. So clearly, it moved up and to the right because this way is up. It got further from this. That makes it upward. And the fact that it moved this way is to the right. If you take a small section of it, like you look and say this little square right here, that's essentially, this small of a square is essentially exactly what you'd see if you look due east. This would be, you know, the highest part of that due east sky that you're looking at, not the zenith, but, you know, up to say 30 degrees in the sky. And this right here would be the typical view of the eastern sky. This would be the typical view of a western sky, so on and so forth. Does that make sense?
Yeah.
And the big thing, notice this, this star right now is directly over Polaris. That's actually, that's called Phaircad. This is Kochab and Phaircad. Those are the two pointer stars, or excuse me, those are the two dipper stars that you can see along with Polaris. So when you're looking for the little dipper, if you're somewhere bright, you're not going to be able to see these stars. You only see Polaris, Kochab, and Phaircad. But the way you find them is these two stars right here in Ursa Major. they form a pointer. It doesn't show on this diagram, it's hard to see, but they form a pointer that points directly to Polaris. So once you find the Big Dipper, look for the front two stars. They're called Merak and Dubhe. There's Dubhe, there's Merak. So Merak's this one right here, and Dubhe's this one right here. If you go from Merak through Dubhe, it'll form a pointer and it points directly to the North Star, even though it doesn't show it there. But notice this star right here, Faircat, is essentially directly over the North Star. So if you want to know what direction a star moves in 1 hour, if it's directly above the North Star, you go bump, and you see that that star moved down and to the right, down and to the left. If you want to see what a star does when it's to the left of Polaris, well, let's use that same star again because it's so convenient. So I'm just going to keep pushing this around. Boy, this computer's really slow. Get off there.
So it is from our point of view. So like if it looks like it's going down, it's going down.
Exactly.
Okay.
Okay. So if I wanted to see what a star does when it's to the left of Polaris, I just keep moving until one of those stars I like is directly to the left of Polaris. Like right now, Kochab is. So Kochab, the top Dipper star, the top front Dipper star of Ursa Minor, is now to the left of Polaris. And if I want to know what's going to happen in 1 hour, I click +1, and I see that it did move to the right and down. Now notice that's down. Look at it this way. Yeah. So are y'all seeing why I just paused there for a second? Does anybody get why I just paused?
No.
I said the star went down and to the right, which is accurate from the way we're looking. But notice, if you remember, I said this little square right here is a view of the north. So technically, if I'm looking at it, then that is actually to the right of Polaris, and it's going up and to the right. But the way I looked at it is something to the left of Polaris went down and to the right. Both are correct. That's the good thing. It doesn't hurt you either way. But really, if I wanted to say what did it happen from Earth, I should be pretending I'm standing upside down right here. So my head would be here and my feet would be down here, and looking up, and then I'd see to the right of Polaris is where that star just was. So I go back an hour. See, now this star, according to a person standing down here, is to the right of Polaris. According to me, outside the computer, is to the left of Polaris, but it doesn't matter. You don't have to take time and flip yourself upside down to get that right. It'll still come out right.
Okay.
Okay. So that is a problem in that particular spot, but I didn't even go over that in the actual lab. Good thinking, Caitlin.
So my other questions were math-based. So let me go back to, oh gosh. Okay, so these are both on the practice test and the test. So if you want to change the actual numbers in it, of course, that's fine.
Yeah, no
But
problem.
so there were a couple that I don't know if I just missed it or it didn't click or something. But the first one, I have two. The first one is where it says, suppose you were suddenly transported to a planet that had 1/4 the radius of Earth, but the same mass as Earth. And then it's asking what your weight would be by a factor of whatever.
Exactly. Those are good questions, and I'm glad somebody asked it. I hadn't got to describing gravity very well, not on video, so it's really good that I take time to show you that now. So excellent question. I'm so glad you asked it. Let me give you the rundown. So I'm going to show you my document camera again, and this time I'm going to actually talk about gravity. So what happened was Newton, having been sent home for the plague, was according to him, sitting under an apple tree when he looked up and he saw the moon in the distance and a nearby apple and thought how they were related. What he meant by that was the apple was eventually going to fall off the tree, and that's going to take an object that is basically has some inertia, as Galileo had already taught, that and therefore has no intention of moving, and all of a sudden it's going to move and go towards the ground. He said, I think the force that does that to the apple is exactly the same as the force that causes the moon to not move in a straight line, because everybody understood that the moon was actually going around the Earth in roughly a circle. So what he did was this. He said, all right, well, here's the Earth. And then about 60 Earth radii, which this is supposed to be the symbol for Earth, R with a little circle with a plus on it. About 60 of these away is the moon. So this distance from the center here to the center of the moon is about 60 Earth radii. Okay, well, you actually can derive this formula with calculus very easy, but they also do it with just basic algebra. But it turns out if an object really is going to travel in a perfect circle, which obviously the moon doesn't do a perfect circle, but pretty close, then it has to have an acceleration given by, and I'm going to write this stuff. You don't have to know these you don't have to know most of these equations. You don't have to know any of this algebra. I'm just trying to give you an idea where it came from. We know that the acceleration, it must have what we call centripetal acceleration for it to actually go this far, and then of course accelerate towards the center of the Earth just enough so it stays the same 60 Earth radii away, is equal to the velocity of the planet, in this case a moon, squared divided by the distance between them, which in this case would be 60 Earth radii. Okay, he knew that's what the acceleration had to be. He calculated what that is, and it's not too hard to do. You know, velocity is distance divided by time. We know that the moon goes from here all the way around here in about 30 days. So you can use that as a time, convert it to seconds, of course. And you know the distance around is the circumference of a circle, so you do 2 pi times the radius, which is 60 times the radius of the Earth, and you immediately got the velocity. Divide this in, and you get a really small number, but it's kind of interesting to know what number you get. Let me turn my calculator on real quick. I haven't done this, didn't do this calculation recently, so we'll see. You get an acceleration of 0.0027. That's what Newton got, and that's meters per second every second. That can be written meters per second squared as your book does, but I just want you to understand it's better to read acceleration as meters per second because that tells you how much it speeds up every second. So if you drop the moon, it would go 0 meters per second the instant you dropped it, but 1 second later it'd be going 0.0027 meters per second. And then after 2 seconds, it'd be going twice that fast. And after 3 seconds, it'd be going 3 times that fast, so on and so forth. So that's kind of interesting. Now, here's the other thing. Newton said, all right, if that is the force, I wonder how what parameters it depends on. So he just, as a guess, said, I suspect, because he'd been working with optics and light, the brightness of light falls off as 1 over the distance squared. So he said, I wonder if this force of gravity is like 1 over the distance squared. Okay, this little symbol just means proportional to. In other words, there's constants that I can put in here, or constants and variables I can put in here, and then I'd make that into an equals. He said, well, if that's the case, if it is a 1 over r squared force, then the force that I'd have here at the surface would cause an acceleration of 9.8 meters per second per second. We know that for a fact. That's the acceleration due to gravity. He said, therefore, if I actually went out 60 Earth radii, I would expect the force, or in case, since we're working now with the acceleration would be 9.8 meters per second divided by, since I'm not doubling the distance, I'm actually multiplying it by 60, and it's not the distance by itself, it's distance squared. I have to do 60 squared. And when he did that math, he got 0.0027 meters per second per second. At that instant, Newton was the only person on planet Earth that knew exactly why the moon orbited the Earth, why the planets orbit the sun, so on and so forth. So what he found was that the law of gravity is inversely proportional to the square of the distance between them. There were experiments to be done, but in the end, the universal law of gravitation became F equals some constant, G, times 1 of the masses, like in our case, it'd be the mass of the Earth times the mass of the moon. So that's M2 over r squared. And this number, by the way, is super, super, super teeny. It's 6.67 times 10 to the negative 11th. So it's literally a zero, a decimal point, 10 zeros followed by a 667. And of course, the units would be Newton meters squared per kilogram squared. Okay, so it's a really small value. That's why gravity is actually notoriously weak. But there's a key thing that we use when we're talking about equations. If I have an equation, for instance, y equals some constant times x, I see that y and x, there's no fractions present, but y and x are definitely on opposite sides of the equal sign. I can always make a fraction by dividing something by 1. Now I see that y and x are in fact on opposite sides of the equal sign, but on the same side of the fraction bars. So they're both numerators. Well, that's what we call thumbs up, okay? And that's the way I want you to think about these things. Whenever you have two variables on opposite sides of the equal symbol, but both are in the numerator, that means thumbs up, which says, hey, if I double x, then y is going to double. If I triple, notice I'm multiplying here, I'm not adding. If I triple x, I triple y. If I increase x by a factor of 3.14, I increase y by a factor of 3.14. So that's what we call directly related. You may have ran into this in algebra before, but I don't want you doing any math to do this. I just want you to think thumbs up. And if I can figure out by what factor one of the variables changed, then I'll immediately know by what factor the other variable will change. There's another one though. If I said y is equal to k2 over x, in this case, the x and the y are still on opposite sides of the equal sign, so that's a good check. But the problem is the y is in the numerator and the x is in the denominator. They're what we call thumbs up, thumbs down. Oh, it's really hard to do this. Keep it this way. Okay, thumbs up, thumbs down. Okay, so what that means, if x goes up by a factor of 2, y goes down by a factor of 2. Or if x goes up by a factor of 7, y goes down by a factor of 7. Or if x goes down by a factor of 3, y goes up by a factor of 3. This is called indirectly related. Indirectly or inversely. Okay, now we have all the tools we need to understand Newton's law of gravity. Newton's law of gravity says that the force of mutual gravitation, remember Newton's third law says, if this guy puts a force on this moon, then the moon puts exactly the same force back on the Earth, but in the opposite direction. So the moon is pulling the Earth that way, and the Earth is pulling the moon this way with exactly the same force. Problem is, F equals ma says because the mass of the Earth is so much bigger than the moon, it's not going to move very much, whereas the moon's going to move quite a bit. So when I look at this, I say F is directly proportional to m1, or directly related. So if I double the mass of the Earth, I know the force of gravity on the moon would double. If I tripled the mass of the moon, I know the force of gravity on the moon would triple. If I did both, if I doubled m1 and tripled m2, then the force of gravity would do what? I doubled one and I tripled the other. Well, you're first going to multiply by 2 for doubling, right?
Mm.
What are you going to do to the force for tripling?
You're going down.
2 is multiplying by 2, so that's getting bigger. See, F and M are on the same sides of the numerator. So they're like directly proportional.
Yeah.
So if this one doubles, I'm going to have to multiply F by 2. If this one triples, I'm going to have to multiply F by 3. So in the end, I'm going to have to multiply F by 2 and then by 3, or F will go up by a factor of 2 times 3?
6.
There you go. So that's the way you work that far as the mass ones. That's not the question you asked. The one you asked was more about this other one. So let me explain what this one does. This one's kind of weird. So F and R, notice they're like this. One's in the numerator, namely the F, and the other one's in the denominator, namely the R squared, but it's squared. That's a lot different than this guy. So there's something funny going on here. So yes, one is thumbs up and the other one's thumbs down. So if the radius goes up, in other words, the distance between the two planets or the two objects goes up, the F will go down. But here's the weird part. If I double R, I'm not doubling R squared, I'm doubling R, and that means R squared increases by a factor of 2 times 2, or 4. So when I double R, which means R is going up, F is going to go down by a factor of 2 squared, or 4. So here's the trick. Let's say M1 goes up by a factor of 2. That means F is going to go up by a factor of 2. If M2 goes down by a factor of 7, then F is going to go down by a factor of 7. If M1 goes up by a factor of 2 and M2 goes up by a factor of 3, that's going to cause F to go up by a factor of 2 times 3, which equals 6. Okay? Now, dealing with just the R's, if R goes up by a factor of 2, then F, since they're thumbs up, thumbs down, will go down. Okay, notice the up and down, and this is the up and up and down and down. So this will go up not or down not by 2, but by 2 squared, which equals 4. If R goes down by a factor of, say, 3, then F is going to go which way, up or down?
Up.
Up, exactly. And not by 3, but by
3 squared.
3 squared, which is 9. Okay. And if R goes, let's say, up by a factor of 4, then F is going to go
Down by
by a factor of
16.
16. Very good. Okay, so that's the way I want you guys to treat gravity and this stuff. I don't want you, plugging in that god-awful number and looking up the masses of the moon and the Earth, or the moon and you, or whatever. What you want to do is think about it this way. So your question, for instance, asked, what would be our weight if the moon, if the Earth did what?
It was if you went to the moon, which has let me actually look at it. Suppose you were suddenly transported to a planet that had 1/4 the radius of Earth, but
Gotcha.
the same mass as Earth.
So the same mass of the Earth, but 1/4 the radius?
Yeah.
Okay, so first off, let me show you what's going on here. So Newton's second law, which I normally write like this, your book didn't. I put this little sigma on there. You guys are in college, you know that if you graduate summa cum laude, that's really good. Magna cum laude is almost as good, and cum laude is almost as good as magna cum laude. So the summa came from this Greek symbol, and this Greek symbol is used to say add up all the forces. So I just do this to remind students you can't just take a particular force and apply it in Newton's second law. You have to take all the forces acting on a body of mass m, and that will give you an acceleration a, like this. Okay, so in order for you not to do algebra, I introduced the little circle here. So what I'm going to do is say the total force, and that's another way you can read that. Instead of saying sum of forces, you say the total force is mass times acceleration. So if you wish to solve for mass, you cover it up. Oh, it looks like I take the total force and divide by the acceleration. And that's exactly how you do it. If you wish to solve for the acceleration, you take the total force and divide it by the mass. If you wish to solve for the total force, you multiply mass times acceleration. Does that make sense?
Mm-hmm.
So that's Newton's second law. In the case of an object that's falling, which is really what you're trying to figure out, what is the acceleration of gravity, or how much do you weigh, which is related to the acceleration of gravity, what you have is this gravitational force, G, mass of Earth, which again, that's the symbol for Earth, times the mass of you, over 1/4 of the radius of the Earth. Of course, that's all squared again. And that's equal to the mass of u times gravitational acceleration, which is g. Okay, that's really what's going on here with the problem you asked about. But the good news is you don't have to work all this junk out. All you really need to understand is, oh, this is going to cancel out with that. So really what matters is gravitational acceleration is just related to gm over r squared. So gravitational acceleration is just this part without one of the masses. So boom, there's your 9.8. If you looked up the mass of the Earth and plugged it in there, and looked up the radius of the Earth and plugged it in there and squared it and multiplied it by that 6.67 times 10 to the negative 11th, you'd get roughly 9.8. So you don't have to do that. I'm just saying that's kind of neat to know. So now you know the acceleration due to gravity and in fact your weight are both dependent on 1 over the distance squared. So if the radius went down by a factor of 4, that's just like this problem, only it went down. What's the force going to do? Go up or down?
Up.
Mm-hmm. And by how much?
16.
Exactly. So if you were 100 pounds on Earth, you're going to be 1,600 pounds there, which is about as much as an F-150 weighs.
Okay.
So yeah, that's pretty heavy. I'd be needing to eat a salad. Does that make sense?
Yeah. So even though it says like 1/4, we're still going down.
Exactly.
Like,
I know my students don't like fractions, so I always keep it as a whole number. When they say something's going down by 1/4, they really are meaning you're dividing it by 4. So I only use, if I want to get something smaller, I divide by a big number. In other words, a number bigger than 1. If I want to get something larger, I multiply by a number bigger than 1. So no matter what fraction they're doing, you got to decide whether it's going up or going down, and then by what factor, and you don't want to use fractions. You can use them. I mean, if you actually work this out, you see that it does, in fact, multiply by 4, because, a fraction divided by a fraction is basically the original fraction times 1 over this fraction. So that would actually work, but that's complicated. You don't want to do that mess.
Okay.
Okay.
And the second question that stumped me, which I think may kind of fall into all this math as well, but it was, if you weighed 100 pounds on Earth, what would you weigh at the upper atmosphere of Jupiter? For reference, Jupiter has a mass that is about 300 times Earth's mass and a radius that is 10 times Earth's radius.
Okay. So what we're doing is the force on Earth is 100 pounds. Okay. And we know that Newton's law of gravity is G m1 m2 over r squared. Or if we really want to know what our weight is our mass, which would be mu times g, which is mu times g m Earth over r Earth squared. So that's really what's going on. Weight is always m times g. That's another circle I can give you, by the way. Weight, m, and g. So if someone gives you your weight, which is measured in newtons, by the way, okay? Newtons, not pounds. We use newtons in this class. And by the way, a pound is a unit of force, whereas a kilogram is a unit of mass, and a slug is a unit of mass in our system. But if you want to solve for m, you cover it up, you get w over g, so on and so forth. Hold up. Had to sneeze. So we know that's what's going on. Thank you. We know that's what's going on. But what we also know is that the mass of Jupiter, or the mass of one of them, say M1, is going up by a factor of 300. Okay? But we also know the radius went up by how much?
So, yeah, Jupiter has a mass that is 300 times Earth and a radius that is 10 times Earth.
Okay, so I've got it now set up like these things, right? So M and F are thumbs up, right?
Mm.
So that tells me F is going to go up by a factor of 300. But R and F are thumbs up, thumbs down.
Mm.
So it's also going to go down by a factor of what?
100.
100. So what you're going to do, remember I told you if you want to make something bigger, you multiply by a number bigger than 1. And if you want to make something smaller, you divide by a number bigger than 1. So what you're going to do is you're going to multiply by 300. And then you're going to divide by 100. And I think you can see that's equivalent to F going up by a factor of 3. So your weight on Jupiter be 300 pounds. Okay.
Wait. Oh, okay.
Yeah, because I multiplied it by the 100 that we were originally given. I think that's what we were given. So, and that is true. It's actually I think it's 29.7 meters per second is the acceleration due to gravity on Jupiter.
Okay.
Just one more to make sure you guys are up to speed on how to do this. What if I told you M1 went up by a factor of 20, M2 went up by a factor of 100? No, let's do that. Let's do 5 by a factor of 5. But at the same time, R went up by a factor of 10. What's going to happen to the force of gravity? So I could give you a number. I could say the force of gravity right now is, 1,000 newtons or 42,000 pounds or whatever I wanted to. And all you do is just do the same stuff I've been doing with all these arrows and stuff. But then in the end, you multiply the result times the number I gave you. Or I could just ask you this, and you just tell me what the result is by, drawing an arrow. So what is M1 going up by 20 and M2 going up by 5 going to do?
The force is going to go up by 25.
Not 20, yeah,
Yeah.
you figured it out, right? By what?
Oh, wait. Is
She
it?
added. You don't want to
Yeah.
add, you want to do what?
My bad.
No, that's normal. Everybody does that. I'm glad somebody made the mistake. That's good.
Yeah, it's going up by 100.
Exactly. Okay. So yeah, you always multiply. So 20 times 5 is 100. Now, when R goes up, what happens to F?
It goes down
So how much is it going to go down by?
100.
Ain't that cool? So you see the answer is just going to be F is the same. That's a really big deal. In fact, this 1 over R squared thing that gravity behaves by, I told you light did. That's what Newton had the idea. It's also very important because one time someone asked, Einstein, when he wrote his 1905 paper, he became famous in the physics community. But in 1915, when he when he wrote his paper on general relativity, he got a little more famous in the physics community. But when the actual experiment went down, where he predicted the bending of starlight, he became like super famous. Like, he was being asked to come to different countries and give lectures. He at one time had 12 mistresses. I'm not saying in a sexist sort of way that that's a measure of awesomeness, but in some sense, a dude that looks like that got 12 women. There's a reason for it, right? But he was really he was really famous. So they were asking questions about everything. So they asked him, Professor Einstein, what do you think about ESP and telekinesis? ESP is your ability to read minds or something like that, and telekinesis is your ability to move things with your mind. And he said, I don't know, but if you show me that it obeys a 1 over R squared law, then I'll believe it's true. So that gives you an idea that this 1 over R squared is something bigger and deeper than just happens to be what gravity behaves to and what light behaves to. It's in fact a relationship that's very fundamental. It's also that the reason that the brightness of a star is related to the luminosity by 1 over the distance squared. And here's the reason. If you have a little pinpoint of light that's perfectly spherical, or is just infinitesimally small, then it acts like it's perfectly spherical. Then it's going to send them the same amount of light out in every possible direction. So the number of photons that go this way is exactly the same as the number of photons that go this way, is exactly the same as the number of photons that go this, so on and so forth. And I shouldn't have drawn two arrows there. One would have been sufficient. Okay, so what that means, if I go out a distance of 1 meter and make a sphere, and then I do a 1 meter by 1 meter window, and this radius, of course, is also 1 meter. Okay, then every bit of light that comes through this little window will then go through, if I make another one that's twice as big, will then go through another window only this window on the 2 meter sphere this window in a 2 meter sphere will be 2 meters by 2 meters. So let's say 400 photons came through this window. That means the intensity at 1 meter would be 400 photons per 1 square meter. That's intensity means divided by the area. So this would be 400 photons per meter squared. If I looked at the intensity at 2 meters, in other words, the intensity, the same amount of light now, the same 100 photons that went through this window are exactly the photons that went through this window, I would see that now I've got 400 photons, only this time it went through a distance or area of 2 meters times 2 meters, which is 4 square meters, and we get 100 photons per square meter. So you see how doubling the distance away decreased the intensity by a factor of 4. That's why Einstein said that, you know, if you show me ESP or telekinesis abilities falls off as 1 over the distance squared, then I'll believe it's a real thing. Because everything that acts like a pinpoint, which is what a human brain would do compared to the size of the human brain to how far away a person would be, the size of the brain is teeny, so you might as well, you know, assume it's infinitesimal, or at least assume it's a sphere, and you should get something like that. So a lot of things behave this way. For instance, if you have a little speck of americium, or if you have a little speck of cesium laying on a desk, these are radioactive isotopes, or technetium-90, which is one that we sprinkle on eggs and have patients eat so that they can study how quickly their stomach empties. It's called a gastric emptying study. So they'll take and they'll scramble some eggs, they'll literally just stir them up in a bowl, spread this technetium-90 powder on it, and then put it in a microwave. Or actually, they put it in a microwave first, and they spread technetium-90 powder on it, and then you eat it. And then they lay you in front of an X-ray detector. And that X-ray detector moves all around and catches all the radiation coming from your stomach. And slowly, by doing that, they can see how long it takes for that egg to go from your esophagus, from your esophagus into your stomach, and then from your stomach out through your intestines, and so on and so forth. They also inject people with it in their blood, and then they lay them in front of another X-ray detector. And by doing that, they can tell if there's any blockages around the heart. So when you have to deal with such things, maybe you're in nuclear physics or nuclear medicine, then you have a source of technetium-90 laying on your desk. What you realize is the dose of radiation you're getting falls off as 1 over the distance squared, and the dose of radiation you're getting is also directly related to the time. So if you double your time, you double your radiation exposure. If you triple your time, you triple your radiation exposure. So 1 falls off as time. So if I cut the amount of time I'm going to be around the technetium-90 in half, I cut my radiation dose in half. That's a good thing. But check this out. If I can be 1 meter away from the technetium-90 or 2 meters away, if I choose the 2 meters, I can actually cut my dose not by 2, but by 4. So that's super valuable. It's way more important to stay away from a radioactive source by distance as opposed to limiting your time. That's why people go into nuclear power plants after disasters and stuff like that, and they try to limit the amount of time they're in there, and they also want to stay away from certain parts because some parts are just so deadly it's going to kill you no matter what. So it's kind of a neat little sidebar to some of the things that you learn, in physics and astronomy. You now can apply in the everyday world, and it's just like also a simple thing. So I hope that helped as far as you guys understanding how Newton's law of gravity works. Here's another problem that I hadn't talked to you about, but imagine this. Imagine you have an airplane. Okay, there's an airplane. It has a thrust of, let's say, 10,000 newtons. It also has a drag force, in other words, the air resistance force is, let's say, 7,000 newtons. Okay. The weight of the aircraft is, let's say, 10,000 newtons. I would like to know, what is the acceleration of the aircraft? So this is a very typical Newton's second law problem. The good thing is, in our astronomy class, you don't have to deal with vectors. You just have to treat things in one dimension. So as long as things are either parallel or anti-parallel, then you just treat one direction as positive and the other direction as negative, and you're doing all the math that really needs to be done. So Newton's second law, which I told you is the summation of forces equals mass times acceleration, and those arrows indicate that they're actually vectors we're dealing with. So this equation not only gives you the size of the acceleration, it gives you the direction. That's why I put that there. But we're going to use it like this, which is way easier. The total force, mass, acceleration. I want to find the acceleration, so I cover it up and see that the total force is divided by the mass. So A equals the total force divided by the mass. But I wasn't given the mass, I was given the weight. However, I also know that weight is equal to m times g. So if I want to know the mass, I just divide the weight by g. Well, we know g is actually 9.8 meters per second per second. Okay? But I'm going to say it's approximately 10 because that's close enough. Okay, and you can do that with my class and my test. Unless I explicitly tell you to use 9.8, you can roughly get a good estimation of it by using 10. Okay, so if I want to know the mass, I'm going to take the weight and divide it by 10, and that'll give me the mass. So the weight is 10,000. That means the mass is 10,000 divided by 10, or 1,000 kilograms. Now the total force is 10,000 minus 7,000. So that'd be 3,000 newtons. Okay. So 3,000 divided by 1,000 gives you 3 meters per second every second. So with this force and this thrust force and this air drag, the aircraft is able to accelerate at 3 meters per second per second. So that's a typical Newton's second law. One I also do is sometimes I'll say, hey, a bear is sliding down a tree. The friction force between the bear and the tree is this number. The weight of the bear is this number. Now you've got weight as acting as a force that matters. See, this weight didn't matter here because it's perpendicular to the main forces. But in the case of the bear, the weight is sort of taking the place of the thrust, and the friction is sort of taking the place of the air drag. And I ask you how rapidly the bear will slide down the tree. So, the bear is bear hugging the tree. He has a weight of, say, 1,000 newtons, and he's got a friction force of, let's say, 400 newtons. And I ask you, what's the acceleration of the bear? You do it exactly the same way, only now we're dealing with vertical motion instead of horizontal motion. Any questions on that? Does somebody need to see that? Can you think it out in your head? All right, how about any other questions? Anybody have any questions on anything else, material or otherwise? All right, well, You guys are completely free to go if you'd like. I'm going to go ahead and do a discussion on chapter 6 of the TCC book we're using, which is very much related to, I think it's chapter 5 in the other book for the other class. So if y'all want to stick around and watch the discussion, that's great. If not, that's okay too. But feel free to ask questions, and I will go over it. And this will be recorded, of course, and will be posted later. And I'll send you an email probably when it's up, or you can just keep checking back in Canvas or Moodle, depending on where you're at. So let me start by sharing my screen again. I'm going to share it with this PowerPoint. And I'm going to do it in a slideshow format. So hopefully everybody can see that now. Okay. So chapter 6 is the tools of the astronomer. And the textbook gives you the learning goals. Actually, let me read them to you real quick, because that's sort of important pedagogy, is to make sure you understand what your focus is in a chapter as you're going over the chapter, so that you can actually sort of tell what part is me telling you about how we know things and what part's the stuff that we need to quote unquote know. I would generally like to just say you need to know everything, but you know, that's not really realistic to how things work. So what I do try to do is I try to give you an idea of what to focus on a little more pressingly. So the learning goals for this chapter are to compare how the two main types of optical telescopes gather light. They're talking about refracting telescopes and reflecting telescopes. Remember, refraction is from your old high school days when they showed a pencil sitting in a glass of water and it looked like the pencil was broke or bent or something. That's refraction. It takes place when light goes from one material into another. Learning goal 2 is summarize the main types of detectors that are used on telescopes. So we're going to talk about CCDs and stuff like that. Learning goal 3 is explain why some wavelengths of radiation must be observed from high, dry, and remote observatories on Earth or from space. So there is actually some radiation that we like to look at that you literally can't, detect from the ground. And for good reason. It would actually cause us a lot of different problems if it actually reached the ground. Learning goal 4 is explain the benefits of sending spacecraft to study the planets and moons of our solar system. And learning goal 5 is describe other astronomical tools that contribute to the study of the universe. So it turns out, the Large Hadron Collider, which detected the quote-unquote God particle, is very important to astrophysics and astronomy. And the LIGO, the Light Interferometric Gravitational Observatory, which made the first observation of two black holes colliding, is very important to cosmology and astronomy and astrophysics. So that's kind of stuff we're talking about here. So why are most telescopes on remote mountaintops? Well, it turns out it's not because you're closer to the stars, because the Earth's radius is so insignificant to the distance of the stars that clearly being at a high altitude is not relevant. It's actually more because the atmosphere is very thin there, and certain types of radiation can reach only certain depths within our atmosphere. So if you go at the highest points, some of that radiation that you don't get down at sea level, you have access to there. So it's a lot of things, but it is fairly drier up there. It's definitely a thinner atmosphere, less atmospheric disturbances and stuff of that sort. So here's a picture of some cool telescopes. This is the idea for the James Webb Telescope, if I remember correctly. The telescope is astronomers' most important tool. The purpose of telescope is to gather lights of all kinds. What I often tell my students is, if you were like on Survivor, would you rather have a 2 foot deep coffee mug, or would you rather have a 2 foot deep bucket to catch rain? If you're on a show like Survivor, you really need water, right? That's one of the main things to get. And if you had something whose diameter was about that of a coffee cup, even though it's still 2 feet deep, you're not going to be able to hold much water. Similarly, a bucket, which is 2 foot deep but has the diameter of a bucket, that's going to be able to hold a lot more water. So it's very, very good to use a large diameter. That's the same thing with telescopes. The purpose of a telescope is it's a bucket to catch light. So the bigger the diameter of the bucket, the more light it can gather. And we're going to talk about the 3 powers of telescopes, and the most important one in some sense, is the ability to catch as much light as possible. And that, of course, is directly related to the square of the radius or the square of the diameter of the telescope. So we'll get into that a little bit more. There are two types of optical telescope, reflecting and refracting. So reflecting is one that uses at least one major mirror, and it might use some lenses as well, but generally it uses a mirror, whereas refracting uses nothing but lenses. Hans Lipperhey, not Galileo, not Galileo, not Galileo. Okay, Hans Lipperhey invented the telescope in 1608. It was not Galileo. A lot of people teach that. A lot of people learn that from their high school. What Galileo did was he read about it, made it better, and was arguably the first person to turn it to the sky. Thomas Harriot, who's actually a scientist slash doctor in the Roanoke Island mission, i.e. Mania, North Carolina, also seems to have turned it towards the moon around the same time, and maybe even earlier than Galileo did, but nobody knew about it because he was in friggin' Mania, where you didn't have anything that they could send to a newspaper or whatever. So Galileo is the one that gets the credit, but it is kind of interesting that perhaps Thomas Harriot did it right here in the New World beforehand. So the eye, for instance, is a telescope. It's basically a refracting telescope because right here is the lens. This hole, the size of this hole and the hole itself is called the pupil. And the bigger that pupil is, the more light it can gather. That's why when you're driving at night or you're in the dark, your pupils are dilated. But when you're outside in the sun, your pupils are constricted. So, because there's too much light then, and it would actually hurt your eyes a little bit, so it cinches down and makes this hole smaller. The telescope of the eye is not that great of a telescope. It is in some ways. Let me rephrase that. So its resolution, its ability to discern two things as two different things as opposed to just one big blob, is not that impressive. So think about looking down a long highway, you're driving at night, and you see in the distance a light. When you first see it, it just looks like a single light, and you think, oh, there's a motorcycle coming. But as it gets closer, that light breaks up into two. What happened was there was always two lights, but your eye could not discern that it was two separate lights until they got a certain distance away. That tells you your resolution for your eyeball. In other words, that tells you how small the angle has to be between the two things in order for you to see them as two separate things. It turns out the eye can has about 1 arc a minute of resolution, and the smaller that number is, the better it is. But our number is not that big. It's basically a 60th of a degree, or roughly 1/30th of the moon's diameter. So in that sense, our eye's not that good. Telescopes have usually a much better resolution than that. Okay. Now, where it is pretty good is it's actually pretty good at catching photons. So the cones and rods in the back of your eye, the cones catch color and the rods catch just light without really recognizing color. The cones and rods are very, very efficient at absorbing photons. And in that sense, they're comparable to modern day electronics, or maybe even superior to it. But in every other way, they're horrible. For instance, we evolved out of a thing that was more or less, there was a raised spot on, you can imagine like a raised spot on a side of a fish. Well, if it had the ability to detect lightness and darkness, that raised spot could actually save that creature from being eaten by something, right? So that's something that would give it an evolutionary advantage. And maybe over time that would actually develop into an eyeball. And that's what we believe evolutionarily happened to us, is we probably had a raised spot that just detected light. And when you have such a raised spot, the detectors need to point out towards the raising. Slowly it formed into an eyeball, but it can't redesign things after the fact. So the weird part is our retina is full of these rods and cones, and they all point towards our brain instead of towards the light source. It's sort of like watching TV through the wires. Like if your TV screen was actually, where you could see it from either side, imagine opening up the back of your TV and trying to watch it through all the wires and machinery. That's the way our eyes are seeing, because the capillaries and all that stuff are all in front of the detectors. So that's another reason that we're not that good of telescopes in our eyeballs. Okay. So it collects a limited amount of light, and the eye suffers from relatively poor angular resolution. We'll learn later there's equations to this. I don't make you learn the equations. I'm just going to give you thumbs up, thumbs down type things. This is what refraction means. So if you have light shining, say in the air, and then all of a sudden the flank, you can imagine these as people marching. So here's a line of marchers, here's a line of marchers, here's a line of marchers, and they're going this way. As this flank over here starts to enter the slower medium, maybe this is, say, walking on concrete, and this is walking in the sand, these guys on the end have to slow down. And that's really what happens to light. When light enters glass, it has to slow down. It slows down by a factor of about 1.5. So when it does that, these start to slow down. That causes the whole thing to shift angles, and that's called refraction. So the angle here is the angle of incidence. If you drew another vertical line right here, that would be the angle of refraction. And then the light goes through straight, straight, straight. Then all of a sudden, those marchers, they actually hit the concrete first on this side. So now they start speeding up, which actually pulls them back to the original direction they were going. Again, the angle of refraction, which was this one, now we have as an angle of incidence, and this is the angle of refraction. That's because we went from a slow medium to a fast one. The angle actually got bigger. So when you go from a fast medium to a slow medium, the angle gets smaller, and when you go from a slow medium to a fast medium, the angle gets bigger. That's what refraction is. Again, it's the classic photograph of a pencil sitting in a glass of water looking like it broke. Or if you look from the edge of a pool and you see a penny on the bottom, the pool looks less deep. That's another result of refraction. That covers the details of why that's there. Now, when light goes through glass, it's going to change, and this is a typical shape of a lens that we'd use in a telescope. And there's some neat things. If it goes dead through the center, in other words, through the symmetry axis, it suffers no deflection whatsoever. It'll go straight. If, however, it comes in parallel to the axis, but not through the center, then that light will be focused at a focal point, which is from here to here is a distance called the focal length. So all these things are all going back to the focus, as is that one that was undeflected. So when you do that, you realize, oh, okay, all the light is going to be focused here, and that's the focal length. Now, if you take that image and you examine it right there, it would be very, very small and not that useful. But if you put yet another lens back here, you could actually magnify that image. The only thing is that image is going to be blurry unless the focal point of this object is right at the focus of this object. So in other words, these focal points of the primary lens and of the eyepiece have to be at the same spot. So you can start to see already, if I make a long focal length lens, then my telescope's going to have to be super, super long, because the sum of the two focal lengths has to be the length of the actual refracting telescope. So this one's called the primary lens or objective lens. This hole that the light comes into is called the aperture. And it turns out the longer the focal length, the better. And you'll see in a few slides why. But generally speaking, refracting telescopes have a few disadvantages. One, this piece of glass has to be perfectly pristine. It can't have any bubbles in it or flecks of dirt or anything like that. Both sides have to be perfectly polished to exactly the right shape. So it's two sides that have to be polished. And when you start to get telescopes that are nice, the diameter has to be huge. And you can imagine a diameter of even a meter of glass is going to be heavy. And you're only allowed to secure it to the telescope by the edges, because otherwise you're blocking your image. Okay? So that's some of the negative aspects. Another aspect is called chromatic aberration. It turns out that if you send white light, they sort of look like they all focus on the same point. Notice how the focal point's not that clearly demarcated. It doesn't, like, all the rays don't disappear right here. The reason why is certain colors go here and other colors go here and then other colors go here. In other words, the focal point is dependent on the wavelength of the light. And that's called chromatic aberration. And in order to minimize that, you got to make the focal length really, really long, and still you have a little rainbow around the edges. So that's another downside of it. A further downside of it, this one's kind of neat. Have you ever thought about your rearview mirror, about how that actually works and making the light get darker? you know, it's got that little lever there at the bottom, and you flip it one way or the other, and actually it doesn't matter which way you flip it, as long as you flip it from where it's at to the other position, it always gets darker. Well, the reason that's so is because of this. So I'm going to show you a neat little factoid that you can wow your friends with. So here's a rearview mirror. It's actually a piece of glass that has the back silvered. So this back edge right here is sort of got like a aluminum foil or a silver aluminum type foil coating on the back, or silver or something like that, and they don't use silver anymore. And this would be what your rearview mirror looks like from the side. And it has this little lever down here. Some of them have electronic devices that work differently, but generally speaking, this is what happens. So some jerk behind you is riding with his high beams. And then the angle for reflection, the angle of incidence is equal to the angle of refraction, reflection. So this angle will equal this angle. And it comes back and it hits you right in your eye. And that makes you mad, right? So this is not a ray. This is just a line marking perpendicular to the surface. So it's hitting you right in your eye. But what you can do is you can flip this little lever, and then this glass will go from this position to this red position. So what happens then is the light that came off the red one, I'll draw with blue rays, since the vertical is now like this, or the normal to it is now like this, I have to make this angle equal this angle. So the light now falls on your chest. So that bright light that was directly in your eye, by flipping that lever this way, is now falling on your chest. But watch what happens. The light now goes into the glass like so. It refracts and then bounces off this back surface and then reflects back. And this is the ray you see now. So that's what happens when you flip that lever, is you actually force the light, instead of bouncing off the front surface, you force it to penetrate the glass, refract, bounce off the back edge, refract again on the way out, and come back towards your eye. That little thin sliver of glass took away that much light just because you entered it. So that's another downside of the refracting telescope. The purpose of a telescope is to gather as much light as possible, and refraction steals light. It just steals photons because it has to absorb a certain number of them basically for it to try to pass through it. So that is a neat explanation for why we actually see a darker image when we flip the high beam selector thing on our rearview mirror at night when the high beams are on us. I'm trying to get the slideshow. Okay, so those are the reasons for refracting telescopes being worse. They're super heavy. You have to polish both sides. The glass has to be pristine. You can only hold it by the rear. It's got chromatic aberration, and you really lose a lot of light intensity. You lose photons that you're trying to collect by light entering glass. Okay. Now, here's another reason that the long focal length is good. So if you had an object, like this is the top of an object, that's what the red rays are, and the bottom of the object's the blue rays. So here's my feet. My feet, the image of my feet come in here and then go through the lens and end up over here. The image of the hat on top of my head goes through here and ends up down here. So the image is only this big, right? Now, if I took that same object and now replaced it with a longer focal length, and focal length, by the way, is related to the radius of curvature. It's about half, in fact, of the radius of curvature. So if you made this a spherical mirror, the radius of curvature for this guy would be huge, whereas the radius of curvature for this one would be kind of small. But the focal length is now long. Now look, my rays from my feet end up over here. Rays from my head end up over here. Notice how much bigger that is. So the longer focal length actually makes the image larger, so that's more or less more magnification is a way of looking at it. So that's another reason that refractors with long focal lengths are better. Same thing with reflectors, though. As long as you're using a long focal length, you get a bigger image. So that's another reason to have long focal length. But in a refractor, another reason is the fact about the chromatic aberration. Okay. This is the last serious refracting telescope ever made. It was in the Yerkes Observatory, owned by the University of Chicago. They either just tore it down or put it in mothballs or something because University of Chicago couldn't continue to run it. I really wished it would have been something that they could have made into something for the public. But anyways, this sucker is a 1 meter telescope, and it's like 60 some feet long. You can tell this is a human right here. And you see how many of those humans would it take going end to end to end. And you see, you know, it's a really long telescope. But anyways, that's where you start to see the problems with refracting telescopes. You want them to have a long focal length, so they have less chromatic aberration, but a long focal length means a long telescope. Ergo, you have this big telescope. Okay. So there need to be structures to have, large structures to have a long focal length. The lens suffers from chromatic aberration. The lens actually steals light. You can only secure it by the edges. The two sides have to be polished, so it's super expensive. The glass has to be pristine, all that good stuff. So reflection of light, when traveling from one medium to another, some light will bounce off the surface, reversing its direction of travel, and that's what reflection is. So remember, I just said the angle of incidence is equal to the angle of reflection, but not refraction. So Newton is the one that designed this one. It's called a Newtonian telescope. So his idea is, hey, I can get rid of this chromatic aberration by letting it bounce off of a mirror, because it never refracts then. It's just bouncing off the front surface of a polished mirror. So if I make this mirror polished to the shape of a parabola, which is the ideal scenario, then every bit of light will focus at its focal point, which would be somewhere around here at the tip of that arrow that you're seeing. But instead, if that was the case, he'd have to stand there, which obviously this is small compared to a human. This is, you know, maybe 8 inches long. Obviously, he would be completely in the way. So he said, well, I need to see the light. So he put another mirror on a 45-degree angle and shot it out the end. And then he put an eyepiece, which is, again, a small lens, to zoom in on it. This allows you to fold the ray so the telescope doesn't have to be that big, and you just look through the side. That's a reflecting telescope, and that's a Newtonian reflector. Other telescopes, for instance, can put a mirror that's in this orientation, in other words, it's perpendicular to the beam, and they shoot it through a hole in the mirror in the center, and your eyepiece would be back here. That's called a Cassegrain telescope. But this one's a Newtonian, and looking through the rear, just like a refractor would, is a Cassegrain telescope. So they use at least 2 mirrors. The first one's the primary mirror, just like the other one was the primary lens or the objective lens. You could also call this the objective mirror. And the focal length is determined by the path light takes reflecting off the mirrors. Again, it's sort of like curvature. The big thing is parabola is the best shape. Parabola is the shape that you see those little microphones at an NFL football game or even a college football game. You'll see these plexiglass clear big salad bowl looking things with a microphone mounted in the middle. That's the reason we hear, you know, cuss words and all that stuff from the players on the field, because that mirror is shaped like a parabola, or that salad bowl shaped like a parabola, and they have the microphone at the focal point of the parabola. So all the sound that hits it gets directed right to that, and you're able to see a lot better. In fact, if you go to NC State, they've got 2 I think they're parabolic dishes. They might have just made them spherical, but it's pretty close to parabolic. And they're, you know, a good 50, 75 feet away. And you can sit on this little bench right in front of each one of them. And literally you can whisper and the person at the other end can hear you. It's really kind of cool. So that's kind of the nature of these parabolas. The largest, oh, by the way, so I said it's a parabolic mirror. That's the ultimate thing to do, but it's super expensive to do that. So what we discovered is that you can actually do a spherical mirror, and a spherical mirror is a lot cheaper to make. A parabola takes a lot more work, a lot more polishing and all that good stuff, but you can make a spherical mirror, but then you introduce an error called spherical aberration. So a lot of reflectors actually have spherical aberration, and then they add a little lens out in front to get rid of that spherical aberration. And then it becomes a catadioptric telescope, because it might be a Schmidt Cassegrain, meaning it has a Schmidt lens to help for the spherical aberration or other things, or it might have a Moxitoff lens on the front, then it's a Moxitoff Cassegrain or a Moxitoff Newtonian, so on and so forth. All right, the largest telescopes in the world are reflectors. the reflectors have advantages over refractors. There's no chromatic aberration. Mirrors can be made lighter than lenses. You only have to polish one side. They're more compact. You can actually hold them by the whole back because you don't have to see light through it. So you can secure the whole back. Unlike a lens, you can only hold it around the edges. So here's a table of some of the biggest telescopes. Notice these diameters are in meters. So a meter is about 39 inches, which is about 3 inches bigger than a yard. So we're talking like 45 yards or so for this extremely large telescope. The 30-meter telescope, that's pretty big. You can see Keck 1 and Keck 2 are about 10 meters. That's comparable to basically the Hubble Space Telescope. That's on the order of 3 or 4 meters across. I think it's 4 or something anyways. So these are some ideas of telescopes. The big thing is, yes, large aperture means good telescope. And there's basically 3 powers to the telescope. One power is the least important of all of them, and that's the one that if you go to Walmart or CVS and buy a telescope, they'll be advertising 400 times magnification. Magnification is almost irrelevant to the astronomer. If you're wanting to be a peeping Tom, it might be fairly helpful, which I do not recommend being a peeping Tom. You'll get arrested or beat up or worse. But if you're wanting to actually do astronomy, the more important thing is light gathering ability or light gathering power and resolution. Those are the 2 powers that are most meaningful. So the powers are resolution power, light gathering power, and finally magnification power. Okay, I'm going to use the term resolution power just because I don't like the fact that it trips students up. Let me put it that way. It trips students up to think of some number being small as a good thing. So it turns out resolution is the smallest angle that 2 things can be apart so that you can still see them as 2 separate things. So the smaller you get that resolution, the better it is. What I talk about instead is the resolution power. So if I say it has a lot of resolution power, that means it's got good resolution, okay? So it turns out resolution, the larger the wavelength, the worse the resolution. So resolution and wavelength are thumbs up, thumbs down. Resolution and wavelength of the light you're viewing are thumbs up, thumbs down. So large wavelength generally means bad resolution. But resolution and diameter of the telescope or the aperture, the diameter and resolution are thumbs up, thumbs up. So the bigger the aperture for the telescope, the better the resolution is. And they're 1-to-1. They're not like squared or anything like that. So if I take and go from a 1-meter telescope to a 2-meter telescope, my resolution gets twice as good. Okay. If I go from 1 meter to 10 meters, it gets 10 times as good. So you're seeing it's just like that thumbs up stuff further that we talked about earlier. So the longer the focal length, the better the separation of the objects or features. So a longer focal length also helps resolution. So thumbs up for resolution and focal length. And diffraction is really what we were talking about earlier when we were talking about the limits of wavelength and diameter. Basically, if you had no atmospheric disturbances whatsoever, your telescope would be diffraction limited, and you'd only get that like in outer space, basically. So Hubble's one of the few telescopes that runs on diffraction limit, but it's a good measure. If you know the diffraction limit of a telescope, that's a good measure of how good it is, even though you're never going to get anywhere near that resolution for your telescope from the surface of the Earth. So that diffraction limit, like I said, diffraction limit causes bad resolution when there's high wavelength. So radio waves are horrible, whereas visible light would be better. And resolution power gets better due to the diffraction limit when the diameter of the telescope is bigger. So one of the major hurdles for observing from Earth is what we call seeing. Seeing, or astronomical seeing, just means how turbulent, how crappy, how foggy, whatever the air is. It doesn't have to be cloudy for it to be bad. You can actually have a clear night, but there can be all sorts of turbulence in the atmosphere, heat rising, stuff like that, or hot air rising, I should say. And all of that stuff distorts your image. So we try to find ways of doing that. There's something called adaptive optics. It can actually help. And this picture on the left is one without adaptive optics. The picture on the right is one with the adaptive optics. So now that we have this adaptive optics, we actually have the ability to get pictures almost as good as Hubble does from the surface of the Earth. But we still can't get all the wavelength that Hubble does because Hubble's outside of our atmosphere, and our atmosphere observes certain wavelengths. So the integration time and the quantum efficiency are other parameters for detectors. So our eyeball is like a telescope, but it's also like a detector. We actually have an integration time. There's a certain period of time during which your eyeball is sampling the retina and sending signals to the brain, and then it starts over again. So there's a period that you see stuff for, you know, maybe a hundredth of a second or something like that, and then there's a period where the stuff's being sent to the brain. Then there's a period where you see stuff. Then there's a period where it's being sent to the brain, all that kind of stuff. And you can actually, you know, test this. If you've ever seen, look for a car with like mag wheels, and as it leaves, say, a parking lot, you watch it, especially if it's going perpendicular to the line connecting you and it. As you see the car pass by, when it's speeding up, you'll see the wheels spin faster and faster and faster as the car speeds up. But then all of a sudden, it'll look like it comes to a complete stop. And then it'll look like it'll start going backwards. And then it'll come to a complete stop and go forward. What's happening there is the integration time that you're seeing is not sufficient for you to see that the wheel is continuing to move to the right at a faster speed. So you're actually seeing it, or you're missing seeing it for a big part of the rotation until it appears right back where it was before. That's why it was looking like it wasn't moving at all. And then eventually it gets so fast that you see it not only coming back to where it was, but going a little bit further forward, so you're starting to see it go forward again. So that's a way you can actually detect your integration time. Another thing, and this is the thing that I was talking about, how our eyes are actually pretty good, it's the quantum efficiency, which is the likelihood that a photon falling on the detector will actually produce a response. Our retinas and our cones and rods are pretty quantum efficient. And electronics are maybe, they're good too, but maybe not quite as good. And actually, I haven't read the latest literature on this, so I shouldn't blatantly say it, but at one time, our quantum efficiency was better than the electronics. I'm not sure where it is today, but they're at least comparable. So one of the big things that helped us, not only detectors, but photography. That was the first sort of detector, if you will, that we had. We literally had these photographic plates. You put these chemicals on them that when the light hit them, it would slowly cure them, or sort of melt them actually. And then you wash them off in this fluid, and what was left was all the parts where light didn't hit got basically baked to the glass. So you had a negative, and then you could of course produce the positive from that. But they didn't always do that, because the vast majority of the night sky was black. If you want to actually look at a image of the night sky, it's a lot easier to look at black dots on a white field than it is small white dots on a black field. So they often just left the negatives, and that's how anti-jump cannon and Pickering's quote-unquote computers actually analyze stars and their spectra, as they look directly at the glass plates in negative form. So this was really wonderful. It had increased integration time, so you could, they actually did this top hat trick. So they take a hat and they stick it in front of the aperture of the telescope. They slide the photographic plate in, and of course by doing that, the telescope's shaking like a butt, so it's kind of a pain in the butt. So they just wait till it stops shaking, and then they just pull the hat out of the way, and instantaneously the light would start exposing the photographic plate. And then when you want to stop that, you put the hat back in front of it and pull the photographic plate out while it's shaking, and you keep it in dark and then go expose it or develop it. So that was kind of cool. The problem was it was expensive, slow, messy. Some of those chemicals are not good to breathe or absorb. So we came up with the next device, which is a charge coupled device. This is why you have phones and everything now. Like the new iPhone I have actually has, I think, 4 cameras total. Yeah, I got 3 on the back and 1 on the front. So yeah, this device was created by astrophysicists and engineers working for the government for our ability to detect things from space, specifically spying and stuff like that. And now we've gotten to the point where they can make them so cheaply that we can put 4 of them in a telephone. Well, they're still going to charge you $1,000 or whatever, but anyways, that's why we have so many of these. But the best ones, the best CCDs, are in modern telescope devices, or CCD devices for telescopes. And basically what they are is an array of little like LEDs, you can think of it, where every time well, out of 100 photons that hit a single LED, some fraction of them get recorded as an electronic signal that has not only information about how bright it was, but also around what time period it came. And then that can be shuffled off later, and it's already in computer form, it's already in digital form, so you can stack photos and alter them and stuff like that. So the charge coupled device was a great thing to replace the photographic plates. And it took some time before the charge coupled device had the same resolution that photographic plates did. And in fact, I remember my first digital camera was like a 5 megapixel camera, and you couldn't get as good images as I used to get with my organic film that I used. But once they got about 6 or 9 pixels, I think it actually surpassed the organic film. So now they're super have really good resolution and work a lot better. So the CCD is the astronomer's detector of choice. Spectrographs are other things that are extremely important. You can see this if you just hold up a Blu-ray disc or a DVD or a CD. You'll see rainbows of color bouncing off of it. So those are fine little ridges, almost random ridges in the actual disc. And when light hits that, it's diffracted. Notice I'm saying diffracted, not refracted. When it diffracts, it actually bends different color or reflects different colors of light to different positions. So it actually does the same thing like we used to do with prisms, only now it does it with a diffraction grating. And since it's not going through a prism, you're not losing the brightness like you did with the rear view mirror. So what we do is we take light from a telescope, we basically put a small slit in it so we can have an image to focus on. Then it bounces off the mirror, bounces off a diffraction grating, bounces off another mirror, and then is caught by a CCD and goes to a computer. With that, we're able to get the actual spectra that we talked about in the previous chapters on starlight and quantum mechanics and all that good stuff. So this is basically a map of the electromagnetic spectrum. Great excess undermines various industries. Marxism rules is the mnemonic I gave you guys for that. And all it really means is that basically, if you want a plot of the electromagnetic spectrum, the shortest wavelengths are gamma rays, then X-rays, then ultraviolet, then visible, then infrared, then microwave, and then radio. Okay, but this is a plot of the transparency of the atmosphere, and you see that it's 0% transparent for gamma rays and X-rays, which is good because those are ionizing radiation. Those would be deadly to us. Okay, in the UV, some starts to actually get into the atmosphere. So that's why that little curve goes up there. And of course we get the visible, which is, why we see in the visible probably. Probably we evolved to see what was here. So anyways, you can see once you get out to the infrared, the deeper you go into the atmosphere, there's different levels of absorption by the atmosphere. So different wavelengths you can see of the infrared. But then as you start to get to the microwave, we're back in the opaque area. So the microwave and a good fraction of the infrared is opaque, at least at sea level. And then once we get to radio, we actually get to be transparent again. So that's why we can build Arecibo and Green Bank Radio Observatory and the Very Large Array on the surface of the Earth, because the atmosphere is transparent to them. But remember, they're long wavelengths, so the resolution would be horrible unless their diameter is big. Hence, we have this thing at Arecibo that's like as big across as a football field. So the Very Large Array, you'll see those are not that big. They're a little bit bigger than what you'd see at a cable station or something like that. But their bigness comes from the fact that they are on railroad tracks, so they can roll out and get really far apart. And we have this new technology where we can actually group the signals together, and it's called interferometry. And by doing so, we get basically the resolution of a telescope as big as the distance from the farthest telescope to the other farthest telescope. So literally, if we put one on the surface of the Earth and one on the surface of the Moon with interferometry, we would have basically a 60 Earth radius resolution camera, telescope. So that interferometry has helped us a lot for dealing with radio waves. And since radio waves are so big, you obviously need that or you're not going to get any resolution. So this is why some telescopes just have to be put in space. If you want to see parts of the microwave spectrum, you're going to have to put it in space. If you want to see certain parts of the ultraviolet, you're going to have to at least put it in the upper atmosphere. Same thing with the infrared, and at least in the upper atmosphere, but space might be better. And of course, if you ever want to see X-rays or gamma rays, you're going to have to go to space. So we have the Fermi gamma ray detector, we have the Chandra X-ray detector, and Hubble actually sees in the UV, the visible, and the infrared. All of that because it's in outer space and it can. The Spencer Infrared Telescope is strictly for infrared. And then we have the JCMT, that's actually on a mountaintop, but it can detect the microwaves because it's in a particular part of the microwave that at that altitude we can predict, we can actually detect. So that gives you an idea why that's so. There's the Green Bank on the right and Arecibo, or excuse me, below it. Those are really big telescopes. You can actually tilt that one and aim it in different directions in Green Bank, but you can't do that quite as well when you build one into the side of a valley or down into the dip of a valley. But what you can do is the part that this transducer part that takes the signal can be moved to different places. So you can get a little bit of directionality out of the Arecibo telescope. Not nearly as good as this, but it's still a wonderful telescope. They allow astronomers to study radio waves with wavelengths of about a centimeter to about 10 meters. Radio waves can pass through gas and dust. That's really good because a large part of what we see when we see those dark spots in the Milky Way is gas and dust, whereas these telescopes can actually see right through that gas and dust and can see, for instance, the center of our galaxy in the constellation of Sagittarius. So there's the interferometric arrays. This one happens to be the VLA, and they have several of those, but they improve the resolution by, again, if this is the last telescope, say right here where this arrow is, this is roughly the diameter of the telescope that this one's acting like just by having these all oriented where they are. So, and the farther you put them out, the bigger the apparent diameter is. Now, the big thing is with the interferometry, you do get better resolution, but your light gathering power is still just the same as the sum of the light gathering powers of the telescopes you used. So you don't, you're not getting something for nothing. You still have to lose a little bit by not building the whole telescope that's, you know, a mile across. You're just taking a bunch of small telescopes and putting them a mile apart. We sometimes send aircraft, and there's Sophia there, that can get different types of wavelengths that the low atmosphere definitely blocks, but the upper atmosphere doesn't so much. So you can see satellites in orbit detect wavelengths that the atmosphere blocks, ultraviolet and X-rays, but airborne observatories raise the telescope above the clouds and water vapor, and clouds and water vapor would basically stop the infrared, but because they're above that, the aircraft can actually pick up infrared. They can produce very sharp images, for instance, like the Hubble Space Telescope in outer space has diffraction limiting. Okay, so there's selected space observatories, just telling you about the different ones. One of the things we do is we explore other bodies in our solar system, and ideally we'd like to explore other bodies, period, solar system or not. Obviously there's some problems with that because the nearest star to us is 4.2 light years away. And even if we could travel at, you know, the light speed, that would basically, we would see that craft taking 4.2 years to even get there. But we can't come anywhere near even 1% of the speed of light. So we're really hating it, and they're not going to be able to do that for some time. But there's, you know, a lot of reasons for exploring space. We've used flybys and orbiters, landers, rovers, and atmospheric probes. And we've even, you know, went to the moon, for instance. Hopefully one day we'll go to Mars. But one of the reasons we do it is, one, we learn more about our own planet because we can see things that are similar on other planets and other bodies that are similar to Earth, but act in different ways. For instance, we have, you know, mountains forming on Earth from plate tectonics, but we find other ones that don't necessarily have plates and they still get mountains. So we can see cryovolcanism and sort of cool stuff like that. But also, we don't want to be tied to this planet because it has a finite lifetime. If we want our species to last literally for as long as the universe does, then we're going to have to be able to leave this planet eventually and go to another star system not unlike the movie WALL-E. Other tools for physics are Large Hadron Collider, LIGO, stuff like that. Basically, the Large Hadron Collider and these particle accelerators basically are the only places where we find energies comparable to the energy that we had in the early seconds of the universe after the Big Bang. So if we want to study conditions of the Big Bang, we have to study stuff like this. And I don't know how I just did that. Uh-oh. Okay. Whew. Okay, so anyways, there's gravitational wave detectors. We also have neutrino detectors, as you'll learn when we talk about the sun. The neutrinos were our first way of peeking inside of the core of the sun to make sure we really understood what was going on, and there was this catastrophic failure. But that led to more discoveries, so that's another thing we can use is neutrino detectors. And like I said, LIGO, the gravitational wave detectors. And finally, one of their most important things is computers. We can now run the laws of physics for millions and millions and millions of particles so that we can get an estimate of what happens when two galaxies collide and get images like this. And then lo and behold, we look out in the universe and find there are galaxies that look just like that. So we have an idea of what happened. So that's about it. That's all of this chapter 6. I hope that was somewhat informative. Does anybody have any questions as you're still here?
I'm all set, Professor. I appreciate it, though.
No problem. Like I said, I didn't go too bad. I went about 20 minutes over what I normally do if I did an hour and 15-minute class. So, but we did a lot of private questions. But you guys are free to go. Thanks for sticking around, making it interesting.
Thank you.
Thank you.
Professor.
You're welcome. Have a good day. Have a good weekend.
You too.
Bye-bye.
Bye.